Welcome everyone to section 2.4, where we will be talking about arc length and surface area. And you might not think these two quantities are related, but after this section, you will know why. So the basic premise of what we're doing to start for arc length is, let's say we have some kind of curve, and I want to know the length of the curve. Not just the distance, right, from the start and the stop, but just, if we were walking along this curve, if we were driving on this curve, if this curve were a rocket or something, how far would we have to travel to get from point A to point B? So, we have seen stuff like this before, if we go to Google Maps or something and we want to, see where we start, it doesn't matter the displacement. What matters is the distance traveled. And that's going to be essentially be arc length of this curve. If we wanted to travel, or if we want to look at like how far a rocket's going to have to go, maybe that's going to have to do with fuel or something. We could calculate the length of its travel trajectory. Or if we wanted to know how long a coast was, the coastline of a country or something. As a side note, and I will try to keep this brief, this is super interesting. And you can go down a rabbit hole. There's something called the Coastline Paradox that because coasts are essentially kind of fractal-like in the sense that the smaller and smaller scale you look at a coastline, the more and more like jagged it is essentially. And so it turns out that depending on how you measure the coast, like are you measuring it in terms of meters, or are you measuring it with like centimeters? The shorter the unit of measurement that you measure it by, the longer the coastline is going to be. So if you actually go to an infinitesimal scale, coastlines are infinitely long. Infinitely long arc length is one of the reasons why we're going to be assuming that our function has a continuous derivative. Because if it doesn't have a continuous derivative, you get into some issues like this. If you're curious about fractals, or if this just sounds weird to you, yeah, just read. This is an interesting Wikipedia article. I'm sure there's a bunch of other stuff about the coastline paradox, but it's kind of interesting. So yeah, here we're not only going to require that f is continuous, we're also going to require that f prime is continuous, so that we don't run into any of this sort of tomfoolery. Okay, so that brings us back. Well, how can we come up with a formula? I'm hoping that after the last two sections, three kind of, depending on how you count, you've kind of got an idea of where these formulas are coming from. All of these formulas, to do anything with these curves, we're just looking at little tiny pieces, adding them all up, and seeing what we get. So this one's a little bit more interesting. All right, so again, let's say we're going from A to B. We can approximate this. We're not going to use horizontal lines anymore because that's going to give us into some weird issues. We're going to approximate this with some vertical line or diagonal lines. So let's approximate the arc length like this. We can calculate the length of lines, no problem. And then, we'll just make the intervals smaller and smaller. Those lines are going to get more and more accurate. And then we'll get eventually, assuming certain conditions that are given to us by the fact that f prime is continuous and all this behind the scenes stuff. But here's like the overarching theme of where it comes from for the arc length. So let's look at one of these pieces. Let's enhance, if you will, one of these pieces. Let's look in on this guy. So that's some kind of curve. And we've got this red approximation, this diagonal approximation. And we know this is the point. Let's call this point. Well, let's not call this point anything yet. But the arc length is going to get approximated by this distance. Now let's complete the triangle. It's a right triangle. Again, we want the hypotenuse of the triangle. So what are the other things in the triangle? Well, this is just going to be some small x distance. And this is going to be some small y distance. We could plug in points here and calculate these exactly, but the idea is that it's a small x distance and a small y distance. And that's going to lead to our hypotenuse. which is a small z distance, s distance. S is really common for arc length as a letter. So we'll call it delta S. Z is another really good choice, or C, whatever you want to use for that. So what's the relationship between these two quantities? Well, it's the Pythagorean theorem, right? Delta x squared plus delta y squared equals delta S squared. And again, this is the quantity that we're curious about, because really what we want to do is we want to add up infinitely many of these delta S's. Right, we're adding up each one of these pieces, and then we're saying delta x is going to get smaller and smaller and smaller. Since the function's continuous, that means delta y also gets smaller and smaller and smaller. And as a result of both of those, delta s will get smaller and smaller and smaller. We'll add them all up. That'll turn into an integral with Riemann sums. The book has all of the nitty-gritty details if you want to see those Riemann sums. But we'll just kind of show you where it comes from here. So delta S is just the square root of delta x squared, delta x squared plus delta y squared. Okay, so let's write this as an integral, right? Let's not write things as an integral just yet. Let's factor a little bit. I don't like having two quantities here. I'm going to factor out a delta x squared from everything. I'll tell you why later, but if I factor out a delta x squared, what we're left with is just a 1 when we factor it out of this guy. And this one didn't have it, so to compensate, we're going to have to write this as delta y over delta x. We're going to write it as a change in y divided by a change in x. That should sound a little familiar. And in fact, remember what a derivative is all about. The derivative is a slope of a function. Slope of a function is the slope of the tangent line. And as this gets really small, right, the slope of this tangent line is dy dx. It's delta y over delta x. So as things are eventually going, that's going to approach our derivative. But I'm spoiling it. I'm getting ahead of myself. We know the square root of delta x squared. As long as delta x is positive, which it is, it's just equal. They cancel out. It's just delta x. In general, we usually have an absolute value. I'm going to rewrite this delta s in this fashion. Delta y over delta x squared. Whoa, hold on. I got too many 1 pluses going around here. There we go. There we go. All according to plan. Okay. And then we have a delta x at the end. And remember what our goal is. Our goal is that as delta x gets really small, we want to add up all of these things. Well, that's going to be where our formula comes from. As delta x goes to 0, as our partition becomes finer and finer, what happens? Well, this becomes 1 plus f prime of x squared. And this becomes, this becomes dx. So we just get that integral. So the arc length is going to be the integral from a to b of just the square root of 1 plus f prime of x squared dx. That's how we are going to compute arc length in this class. And again, if you really want the assumptions, we need f to be smooth here. So f is continuous and f prime is continuous. So all this is using Pythagorean theorem and the slope formula, adding them all up, that's an integral. That's a Riemann sum. That's where this formula comes from. We'll use it in the next video. I went completely off of my notes. Is there anything else I wanted to say? No, that's it. That's where it comes from. We'll do some examples in the next video. Good luck. Bye-bye.